Today we are going to discuss the advanced concepts of soil compaction. Compaction is defined as the process of increasing the unit weight of soil by forcing the soil solids into a dense state and reducing the air voids. No significant change in volume of water in the soil. This is achieved by applying static or dynamic load to the soil. Compaction is measured quantitatively in terms of the dry unit weight, that is gamma sub d of the soil. So compaction generally leads to the following desirable effects on soils: increased shear strength, reduced compressibility, and reduced permeability. Principle of compaction and moisture density relationship. You are familiar with that. The typical compaction curve is of this shape, and corresponding to that peak you can get the optimum moisture content, and this is the associated gamma D max. And this is the zero air void line or 100% saturation line. This is a theoretical line, in fact. So in compaction, you can see what is happening. We are going to expel the air from the void spaces, and ultimately, theoretically, you can expel all the air and you can get the two phases of the soil. So in practice, this dry unit weight is never achieved, but it represents theoretical upper bound. So in fact, during compaction, when we expel air from the voids, obviously there will be reduction in the air volume of the air. You must be familiar with this expression, and that is for the dry unit weight of the soil, and you can see the specific gravity of the soil solids, moisture content, degree of saturation, and this is the unit weight of water. And this expression can be used to draw the saturation lines of different percentages like that, and air void lines can be drawn by using this relationship. So keeping this thing in the mind, that the air content here, A sub C, this is volume of air divided by volume of voids, and N sub A, that is the percentage of air voids, that is the volume of air divided by total volume. So saturation line or zero void line, it can be drawn by using this relationship by considering 100% saturation. That means SR is equal to 1. So you are getting this formula. So factor influencing compaction, namely moisture content, soil type, effect of compactive effort. And as far as the compactive effort is concerned, you will have to look at the nature of the effort and the amount of effort. And when you are considering the nature of the effort, so it means the load duration and the area of the contact. These two things are very, very important. Well, the soil type, grain size, shape of soil grains, amount and type of clay mineral present, and the GS of soil solids have a great influence on the gamma D and the optimum moisture content. In poorly graded sands, gamma D initially decreases as the moisture content increases, and then increases to a maximum value with further increase in moisture. At lower moisture content, the capillary tension exhibits the tendency of the soil particles to move around and be compacted. So look at the shape of the compaction curve in different cases: gravel, sand, clay, well-graded sand, sandy clay, pure clay, and here you can see the uniform sand you are having this type. So compactability or ease with which soil can be compacted will depend on the soil type, basically. At a given moisture content, a clay with low plasticity will be stronger than a heavy or high plastic clay, as it will be easier to compact. The reason is attributed to: for a given compactive effort, the air voids can be removed more easily for a low plasticity clay, and because it will have a lower moisture content anyway, a higher dry unit weight can be obtained. So here on this slide, dry density versus water content curves for a range of soil types. So different soils, GW, SW, ML, CL, and CH, we are having the curves like that. And here you can see the 0% air content line. This is 5%, this is 10%. Effect of compactive effort, amount of compactive effort. Maximum dry unit weight increases with increase in compactive effort. Increase in compactive effort decreases optimum moisture content to some extent. Applying more energy to a soil will reduce the air voids content further and increase the dry unit weight. More compaction energy can be beneficial, especially for soils dry of optimum moisture content. So you can see that here you are having the different curves, and you can see that increasing compaction energy, your curve is moving in the upward direction. And here you can see that the maximum dry unit weight has been achieved. If a soil is already moist, weaker, and above OMC, then applying more energy is wasteful, since air can quickly be removed. This point is very important, applying large amounts of energy to a very moist soil may be damaging, since no more air can be expelled, but high pore water pressure can build up, that would cause slope instability during construction, consolidation settlements as they dissipate after construction. So this point is very, very important. Nature of effort, low duration and contact area. Longer time duration leads to reduced shear stiffness response and greater compaction. Greater contact area leads to greater depth of influence. Degree of compaction generally increases with increasing compactive effort. However, beyond a certain point, increased compactive effort produces only very small increase in dry unit weight. That is, it takes a great deal of additional compactive effort, E, to see significant increase in dry unit weight. So here graphically you can see that with the increase of compactive effort, the dry unit weight is going to increase. So here this curve is meant for highly marginal efficiency, low marginal efficiency, and here the moderate. So moisture density relationships of cohesionless soil. So just focusing on the pure cohesionless soils, surface tension induces apparent cohesion surface tension induces apparent cohesive strength, resisting compaction initially, decreasing in dry density. So look at that. So here you can see A point, B point and the C point. A means nearing saturation, B means dry, and C is moist. You can see here the soil is dry, so B point is there, and C the soil is moist, and at A you can see the soil is fully saturated or near to saturated condition. Effect of compaction on soil structure. You can see this is a typical compaction curve that we are having in the case of soil. So you can see that on dry side of OMC we are having the flocculated structure, and on wet side of OMC we are having the dispersed structure. But you can see one thing, that when you are having the flocculated structure, high strength, more coefficient of permeability, less shrinkage, more swelling. And when you are having the dispersed structure, low strength, low coefficient of permeability, more shrinkage and less swelling. If you just look at the dispersion, if your curve is present on this direction, you can say that there is an increase in the dispersion, and if your curve is moving in this direction, so more dispersion is there. So you can see that if your curve is situated somewhere here, so more dispersiveness is there, just more dispersed structure is there. And if your curve is present somewhere here, so more dispersion is there in that case on the wet side of OMC. So effect of compaction on soil structure. At low water contents, attractive forces between clay particles predominate, creating a more or less random orientation of plate-like particles results in low density. The addition of water increases repulsion between particles, leading them to assume more parallel orientation near OMC. If compacted wet of optimum, parallel orientation is further increased, leading to what is described as dispersed structure. Now we will talk about the compaction equipment. In the field, fill soils are typically imported to a site and applied to the existing grade level in layers which are called lifts. When a lift of soil is placed, it will be very loose. Special compaction equipment is then used to compact this lift of the soil. So rollers, rammers and vibrators can be used. So different types of rollers: smooth wheel roller, vibratory roller, pneumatic tire rollers, sheep foot rollers and impact compactors. As far as the rammers are concerned, dropping weight, including piling equipment, internal combustion type and pneumatic type. So we are having these different types of rammers. Now on this particular slide you would find some information about the smooth wheel rollers. Here again some further information is given regarding the smooth wheel roller. Here you would find some information regarding the pneumatic tire roller, rubber tire roller. And here comes the sheep foot roller. Some information is given regarding the sheep foot rollers. Vibrators. Vibrators are two types: out of balance type and pulsating hydraulic type. So here you would find out of balance type vibrator. So we are having such type of mechanism to induce the vibrations. So counter rotating weights are present in that case. Vibrators consist of vibrating unit of either the out of balance weight type or a pulsating hydraulic type mounted on a plate or roller. Vibrators give maximum dry density much in excess of the corresponding compaction test value of OMC. Frequencies range 1500 to 2500 cycles per minute. Impact compaction. It is the transfer of compactive energy into the soil by means of the lifting and falling motion of a non-circular rotating mass. It is thus a process capable of transferring impact loads similar to those found in dynamic compaction on a continuous basis. So features of impact compaction: high energy. The energy rating of the different impact compaction equipments range from 10 kJ to 25 kJ. Higher energy helps to achieve higher maximum dry density that allows to work over a wider range of moisture contents. So high energy, you can see this is a conventional compaction. You are having this type of the behavior, and the impact type of compaction, the curve has been shifted in the upward direction and in the left direction like this. Features of impact compaction: increased depth of influence. Contact stress of impact compactor is 300 kPa to 1200 kPa, exceeding conventional roller, dependent on the soil stiffness. Impact roller's profile radius is not referenced to the center of the drum, greatly exceeding conventional rollers, resulting in a greater contact area. Net result is superior depth of influence, enabling compaction in layer thicknesses exceeding 1 meter. So you can see the depth of influence in case of static pressure and kneading, and this is vibratory energy of low amplitude and high frequency. So you can see that the depth of influence is more in that case. And look at the impact energy of high amplitude and low frequency. So you are having the maximum depth of influence in this. Then comes increased load duration. The impact compactor's load duration has been measured to be approximately 10 to 15 times longer than that of conventional roller. This allows for a softer soil response, and hence enhanced compressibility is attainable. Now look at that increased load duration. What is happening? You can see that with the increase in the load duration, the soil response is reducing. Longer duration results in a reduced soil response and greater compaction can be achieved. So you can see that with increase in the load duration, there will be reduction in the soil response and better compaction can be achieved in that case. High operating speed, that is another feature. Impact compactors operate at speed up to 5 times faster and 10 times greater volume per day than conventional compaction equipment. So here you would find some summary. Smooth field rollers are best suited for sands and gravels. Pneumatic rubber tie roller, silts and clays. Sheep foot roller, silts and clays. Vibratory rollers, sands and gravel. Vibratory tempered sands and gravels. To increase the compaction energy applied to the soil in the field, increase the mass or weight of the compaction equipment, decrease the thickness of lift thickness, and increase number of machinery passes. Field compaction. In general, granular soils can be compacted in thicker layers than silt and clay. Granular soils are usually compacted using kneading, tamping, or vibratory compaction techniques. Cohesive soils usually need kneading, tamping, or impact. Soils such as GW, GP, GM, GC, SW, SP, and SM have good compaction characteristics. Other soils such as SC, CL, and ML are characterized as good to poor. At any rate, the quality of field compaction needs to be assured by measuring the in-situ dry unit weight of the compacted soil at random locations. Field compaction and specification. Two categories of earthwork specification. Number one, end product specification, method specification. With end product specification, a certain relative compaction or percent compaction is specified. Field compaction and specification. Relative compaction is defined as the ratio of field dry unit weight to laboratory maximum dry unit weight, that is gamma D max, according to some specified standard test. So this is the formula for the relative compaction. Difference between relative compaction and relative density. Relative density apply to granular soils only. If some finds are present, it is difficult to decide. ASTM D2049 suggests that the relative density is applicable if the soil contains less than 12% fines. Fines mean passing the number 200 sieve. Otherwise, the compaction test should be used. Densification of granular soils. Engineering properties of cushionless soil are primarily a function of relative density, and you can see the formula for the relative density: maximum void ratio, field void ratio, minimum void ratio. And here you can see the relation between the relative density and the relative compaction. And you can see that when gamma D is 0, that is a pure theoretical case. In that case, the void ratio is approaching to infinity. When the gamma D is minimum, void ratio is maximum. And when gamma D maximum is there, so you are having the minimum void ratio. And when your soil is in between these two limits, so it means you are having gamma D and you are having E, that is E sub F. In the field, the questions that have to be answered are: to what dry unit weight must the soil be compacted, and how can this be achieved efficiently? For many construction applications involving roadways, subgrades, and trench backfills, etc., there are typical standards specifying the minimum relative compaction that must be achieved. Well, relative compaction: fills to support buildings or roadway 90% at least. Top 150 mm subgrade below roadways 95%. Aggregate base material below roadways 95%, and earthen dams 100%. So dry unit weight versus water content indicating the most efficient condition for field compaction. So you can see that the range AC indicated the range at which the soil should be compacted to achieve R sub C at any energy level. Well, when you are considering certain relative compaction, so obviously you can get this range. This is on the dry side of OMC, this is on the wet side of OMC. because this point is corresponding to 100%, and let's say this is corresponding to 95% of gamma d max. So you are having this point and this. So in this way we are having this range from A to C. So in this particular range of moisture content, you could be able to get that desired gamma d, that is here 95%. Field compaction and specification, some important points are written over here. To achieve 95% relative compaction, the placement water content of compacted fill must be greater than water content A and less than C. So this is the range that is from A to C. These points are found where the 95% R sub C line intersects compaction curve. If the placement water content is outside of range A to C, then it will be difficult, if not impossible, to achieve the required percentage of relative compaction. This is why it may be necessary at times to wet or dry the soil prior to rolling. Having established the range of placement water content, it is required now to ask what is the best placement water content to use. Most efficient water content would be optimum moisture content, where the contractor provides the minimum compactive effort to attain the required 95% relative compaction. The most efficient placement water content exists between the OMC lab and OMC obtained in the field. Range of placement water content should also be specified along with relative compaction R sub C. Well, now the other specification, that is the method specification. In method specification, the second category, the type and weight of roller, the number of passes of that roller, as well as the lift thicknesses are specified. This specification requires prior knowledge of the borrow soils so as to be able to predict in advance how many passes of, for example, a certain type of roller will produce adequate compaction performance. Requires test fills before carrying out actual compaction. Method specification is only justified for very large compaction projects such as earth dams. Field density test. The sampling rates for large fills, about 1 sampling per 1000 to 200 square meter per lift. For small fills, that is 1000 square meter, that is 2 to 3 samples per lift. Thus, for a fill with lateral dimensions of 100 meter by 100 meter, one would expect to take 5 to 10 samples measurements per lift. Typical specifications call for a new field test for every 1000 to 300 cubic meter or so, when the borrow material changes significantly. Destructive method involved excavation and removal of some of the fill material, whereas non-destructive tests determine the density and water content of fill indirectly. So destructive methods, we are having sand replacement method or core cutter method. These are the two methods that we are using generally, or rubber balloon method. In non-destructive method, we use a nuclear density method. So field density test, destructive methods are time consuming. Nuclear density method has a high purchase cost, that means the initial cost is high. Safety precautions during nuclear density test have to be followed. So here we will talk about the nuclear density method because you are familiar with the typical methods. Nuclear density method uses a low-level radioactive source that is inserted via a probe into the center of a newly compacted soil layer. The source emits rays through the compacted soil that are captured by a sensor at the bottom surface of the nuclear density device. The intensity of the captured radioactivity is inversely proportional to soil density. The apparatus is calibrated using the sand cone or replacement method for various soils, and it usually provides reliable estimates of moisture content and dry unit weight. The method provides fast results, allowing the user to perform a large number of tests in a short time. In nuclear moisture density method, principal elements are nuclear source emitting gamma rays, detector to pick the gamma rays passing through the soil, counter to determine the rate of gamma rays reaching the detector. Common nuclear sources: radium-beryllium combination, cesium-americium beryllium combination. So these are the combinations which are available. Gamma rays penetrate into soil. Some are absorbed and some reach the detector. Amount of radiation reaching detector is inversely proportional to soil. Nuclear count rate received at the detector compared with the calibration curves provided by manufacturer. Moisture content is obtained from thermal neutron count. Alpha particles are emitted by the source. Americium or radium source bombard a beryllium target emitting fast neutrons. Fast neutrons lose velocity if they strike hydrogen atoms in water molecules. Resulting low velocity neutrons are called thermal neutrons. Moisture results are provided as weight of water per unit volume of soil tested. Dry weight is obtained from subtracting moisture determination from the wet density determination. Significant error occurs if soil contains iron, boron, or cadmium. So there are different methods. First method is direct transmission method, provides more accurate results. Radiation source placed in the test material by using a punched or drilled hole. Depths between 50 mm and 300 mm can be tested. Information surrounding the source is obtained. So this is the schematic diagram of the direct transmission method, and this is the second method, that is backscatter method. Radioactive source and detector located on the surface of soil. Gamma rays directed into the soil and some reflect back to detector. Accuracy suffers if gap exists between bottom of device and soil surface. Information about soil nearest to surface is obtained. So this is the schematic diagram of the backscatter method. And this is the air gap method. You can see that the space is, or you can say the air is there between this equipment and the surface. Less common method and is used when the composition of the near surface material adversely affect the density measurement. So this is the schematic diagram for the air gap method. If the lift thicknesses are too large, then the following will occur. Soil at the top of the fill will be well compacted. Soil at the bottom of the fill will not be compacted. Lift thickness. Well, if you just look at that, when we are compacting one typical layer of the soil, you are having the maximum effect over here and the minimum effect over here and over here. The next lift we are having the same trend that maximum effect of the compaction is at the mid of this. So if you want to attain 95% of gamma D max, so obviously you are somewhere here, and you can see that if you are getting this much, so here you are getting the adequate compaction, but here inadequate compaction is there. If you want to know, if you want to get the 95% of gamma D maximum. So basically this is the density gradient, that means the maximum density over here, you know. The basic idea is that if your density gradient is not crossing this 95% gamma D maximum, so it means you are having the inadequate compaction. But if it is crossing, so it means it's fine. So the compaction is nice. Now here you would find field dry density versus number of passes. So it's quite obvious that with the increase of number of passes, the dry density or the dry unit weight is going to increase. So here, you know, this one is the dry soils, the wetter conditions, and this is corresponding to the natural condition of the soil. So in every case, you know, ultimately you are getting the maximum dry density. And here you can see that the relationship between the number of passes and the dry density. So you can see with the increase of number of passes, the dry density is increasing. And you can see that if the layer of thickness is more, you will be having lesser effect in that case. For most compaction equipment, lift thicknesses should typically be on the order of 150 millimeter. Approximate method for determining lift height requirement or required. Lift thickness should be small enough so that loose layer is not trapped near the interface between fills. So by carrying out the compaction on a trial area, you could be able to get the effective lift height, and that can be used for the compaction of the layers. So in this way you can see you are having first lift and you are having the effect of compaction like this. This is the second one, this is the third layer. So you can see from peak to peak this distance, so you can take this much distance, or you can say thickness, as the thickness of the lift. Okay, here you would find one problem. Given that a water content versus dry unit weight curve is to be drawn, GS is given, standard Proctor compaction, moisture contents and corresponding gamma D values are given. Plot 80% and 100% saturation lines. B part, if it is proposed to secure a relative compaction of 95% in the field, what is the range of water content that can be allowed? And part C, would the 20% air voids curve be the same as the 80% saturation curve? You would find the solution on the next slide. So look at this one. Compaction curve has been drawn, and this is the 100% saturation line or zero air void line, and this line is for the 80% saturation line, and it is just passing through the peak. So saturation line, 100% saturation line, or corresponding to any degree, you can use this one. You can put the moisture content value and the GS value and gamma W, and you can get gamma D. For 100% saturation, you will have to put H sub bar equal to 1. For 80% curve, you will have to put it as 0.8 over here. So from the compaction curve, we have got the gamma D max 17.45 kiloton per cubic meter and OMC 15.17. So relative compaction our gamma sub D field, that is 95% of gamma D max, so that is this one. Range of water content that can be allowed in the field is 10 to 17%. So by using the curve, compaction curve, you can get this one from 10 to 17% corresponding to this value, that is 16.58, because you are having this one on the dry side of MC as well as on the wet side of MC, so this is the range. Okay, if you just look at this one, this relationship, this is used to draw the saturation line. So, and this one is to be used for the air void curve. So you can see here that for moisture content 8.5% and N sub A, that is the percentage of air voids, 0.2, gamma D is 17.22 by using this formula, which is different from 20.56 kilonewton per cubic meter for degree of saturation equal to 80% and moisture content 8.5%. So what does this mean? It means the 20% air void curve is not the same as the 80% saturation line. So that is the conclusion that you can draw from this particular problem. Okay, now in place densification of granular soils, several new techniques such as terraprop method, vibroflotation, building sand compaction piles, blasting, dynamic compaction have been successfully used for compaction in situ soils, especially granular soils. So here you can see the terraprop method works best for shallow water table. Activated vibro driver causes the probe to vibrate in the vertical direction. To achieve soil compaction, the probe is vibrated to the planned depth of penetration. So this is vibro drive. Vibroflotation, when conventional rolling type compaction equipment works the surface of an area, the improvement in density is limited to the superficial zone of deposit. You can say superficial zone of the deposit, typically depth below a meter or two, experience a little or no increase in density. Vibroflotation equipment operates from ground surface, but it can densify the full depth of granular deposit, which are as deep as 12 meters. So for the vibroflotation, this particular part is the most desirable range, representing the most desirable range of particle size distribution suitable for densification vibroflotation. So if your soil is falling in this, so that soil can be best compacted by vibroflotation. Vibroflotation involves the use of a device called vibrofloat, which is a cylindrical piece of equipment about 2 meters long, 400 millimeters in diameter, and weighing about 17.8 kilonewton. The eccentric weight inside the cylinder develops a centrifugal force of about 89 kilonewton at 1800 rpm. The device has water jets at top and bottom. These have a flow rate of 0.23 to 0.3 cubic meter per minute at a pressure of 415 to 550 kilonewton per square meter. The vibrofloat sinks into the ground at the rate of 1 to 2 meters per minute. When the desired depth is reached, the top jet is turned off. The device is then withdrawn at the rate of 0.3 meters per minute generally, and sand is added from the top. In a regular working day, a compaction of 2550 to 5100 cubic meter is not uncommon. So here you can see the schematic diagram showing the operation of the vibroflotation. So this is the case at start. Lower jet is open fully. Water is introduced more rapidly than it can drain away. This creates a momentary quick condition ahead of the equipment which permits the vibrating machine to settle of its own weight to the desired depth. In this way, the vibrations can be induced at the desired depth. The water from the lower jet is transferred to the top jets and the pressure and the volume are reduced just enough to carry the sand to the bottom of the hole. The sand is being placed into the hole. Actual compaction takes place during intervals between 0.3 meter lifts which are made in returning the vibroflow to the surface. The vibrator is first allowed to operate at the bottom of the crater until the desired density around the lower part of the machine is attained. By raising the vibrator step by step and simultaneously backfilling, the entire depth is compacted. In-place densification of granular soils, blasting or by explosives. The range of soil grain sizes suitable for compacting by blasting method is the same as for vibroflotation. In this method, the compaction is achieved by successive detonations of small explosive charges in saturated soils. Relative densities of 70 to 80% up to a depth of 20 to 25 meter can be achieved. Explosive charges 60% dynamite, 30% special gelatin dynamite and ammonite are most commonly used, are placed at about 2 by 3 times the thickness of the stratum to be densified. The spacings of the charges vary from 3 to 8 meter. 3 to 5 successive detonations of several spaced charges are usually required to achieve the desired compaction. The shock waves due to blasting cause liquefaction of the saturated sand followed by densification. Practically no compaction is achieved in the top 1 meter, and so this zone usually needs recompaction by rollers or by using conventional techniques. The relation for the weight of charge and the sphere of influence for compaction can be given by this, where W is the weight of the charge, R is the sphere of the influence. The radius of the, basically, when we use this technique, there is a theoretical circle will be developed in the horizontal direction, and this R is the radius of that circle. C is the constant, that is 0.0025 for 60% dynamite. If blasting is used in dry or partially saturated soil, pre-flooding is desirable. This is very, very important point. Okay, then comes compaction by pounding, dynamic compaction or high energy impact, used for improving surface and near surface zones of soil and fill material whose existing condition is considered marginal or inadequate foundation support. The method consists of dropping a heavy weight from a relatively great height, weights ranging 2 tons to 15 tons, and drops have a range from 10 to 30 meters. Pounding means repeated heavy blows. Usually, a closely spaced grid pattern is selected for the pounding locations, and the multiple poundings are required at each drop location, typically 5 to 10 drops. It can densify loose cohesionless soils, fracture and densify buried building rubble such as that which exists at old building sites, consolidate fine-grained soils, and compact buried garbage fills. And here you can see the arrangement that we are having for that pounding action. The pounding creates a depression at each drop location and also produces an aerial settlement. So in this way, these heavy weights will be dropped and this whole area can be compacted. So that's all for today. Thank you.